Hello, everyone. In this recording, I wish to dive into a little more deeper into fundamental theorem of calculus part 1. Okay, I had some discussions with some of you, and that was very, very helpful. And I wish to thank those individuals who have raised the question. So first of all, I'd like to show you what it is. What is F? What is G? How is G generated? Okay, so the first part, I choose a function. This function is as such, plus 3. Okay, plus 3. So this is the function. Okay, so this is minus 1. Okay, so that's the picture. The picture of this function goes like this. Okay, x minus 2. This is a parabola. I chose this function that was in its parabola form. Okay, is t minus 2 squared plus 3. In expanded form is minus t squared plus 4t minus 1. We're discussing from 0 to 4. So the interval is 0 to 4. That's our A to B. Okay, A to B is 0 to 4. And that's our F of t. D is constructed according to that definition. Okay, integral from 0 to x, right? So we're going to integrating this function. So from 0 to x, right? We choose the x to be between 0 and 4. Okay, and next, let's see what happens. When we choose, let's take some example, right? If I choose x equals to 1, so g of 1 will be equal to this integration from 0 to 1. What would that be? If we plug in the function, right? F of t will be that piece, and we can find its antiderivative. So we can use the fundamental theorem of calculus part 1 to find its value. Okay, so and in this case, we will get a number. Okay, from 0 to 1. From 0 to 1, so the antiderivative of the inside of the parentheses would be it's negative t squared, t to the power 3 divided by 3 plus 2t squared, right? Minus t. And all of these will be evaluated at 0 and 1. Right? So that's the fundamental theorem of calculus part 2. And we're getting a number. And what's that number? Well, if we plug in the 1, so all of these t replaced by 1. Subtracting on all of that, t is replaced by 0. Right, so I'm just following the fundamental theorem of calculus part 2 and do the replacement. And in the end, we're getting a number. Of course, all of these will be 0, and all of these will give us a number. And that number is going to be, okay, I'm going to be lazy. So 2/3. If you plug in g of You do other numbers. Of course, you can repeat this process for any value, right? You can repeat this process for any value. Say, I'm going to choose 1.2. Why not 1.2? Right? You don't only just choose, you not only just choose the integers or the nice and neat numbers, you'd be choosing, other numbers, right? 1.2. So I'm going to choose 1.2 here, 1.2 here, and 1.2 here. And now, so this piece is going to be calculated. I will get another value, 1.104. You can see D. You can see G of 1, right? When this X is 1, this X is 1, we get a number. Okay, so let me make a table to show you. Column, right? For G, the G function, when X equals to 1, G of 1 look like this. So G of 1, so this is a 1, consistent, they're consistent, right? That equals to, we have a value which is 2/3. For each input, there's an output, right? For X equals to 1.2, we have another G. And this is a G, this time is G of 1.2. G of 1.2, right? And we get another number, which is 1.104. For each input, there's exactly one output. Does that sound like a function? So G is a function of X. Okay, G is a function of X. Okay, you can do a few more. Say I can do, let's do a G of 2, right? If I do G of 2, all this process is repeated, but this time is G of 2. So this is going to be 2. This is going to be 2, right? And the antiderivative stay the same. So this is going to be replaced by 2, replaced by 2, replaced by 2. And then, the lower limit is still 0. So that we got this number. And I put in my calculator, I get 10/3. So when I have G of 2, right? When X equals to, wait. Oh, never mind. G of 2, when X equals to 2, G of 2. What is G of 2? G of 2 is this piece. G of 2 is this piece. And what do we get? After we do this integration, we get 10/3. We get 10/3. Okay, we don't need that other column. So we keep going, and we know that there are infinite number of numbers. So, we didn't do 0, right? We could do 0, why not? Right, we could do 0. We insert a row, right? When X equals 0, what happened when G of 0? Well, for G of 0 this is 0, and that is 0. And from 0 to 0, and that area is 0. Okay, what does this all say? What does this all say? Okay, I'm going to show you with this picture. I'm going to show you with this picture. This is the picture. Okay, this is the picture of the graph. I'm going to put it right here. Maybe I should, now I think of something to do. Okay, so I'm going to insert a column. I'm going to put my little picture right there. Okay, for 0, 0, so we're basically integrating. So this is the picture. Okay, I'm afraid that this may not be a good idea to show. Okay, so from 0 to 0. Okay, never mind. I'm going to do this. For 0, 0, it is an area between from 0 to 0. That's easy to understand. So let's look at, I'm going to take that picture with me. For G of 0, 0, we're done. G of 1. What is the implication? What is the implication? Right? From 0 to 1 is the area beneath the area between the curve and x-axis is from 0, right? So I'm going to mark 0, 0. That red dot to, let me make it red. Make it red. So the area underneath the curve from 0 to 1, right here, right? So another point, 1, 0 is a red dot. And what it means that for G of 1, G of 1 is the area between the curve and the x-axis. So it covers this area and that area. Okay, and of course there's cancellation takes place. The cancellation. So G of 1 from 0 to 1, that area is the sum of these two shaded parts. Okay, and now clear that up. Right? How about from 1 to, from here to 1.2, 0 to 1.2. That's the area on between the curve and x-axis. This time, the point is not is going to be 1.2. Okay, so what are the area? The area between 1.2 and 0. So these areas. Okay, so this little area plus this area. Okay, so that G of 1.2 is that area. So we keep going, we can do 1.2, 1.3, 1.4, all the way to 1.2, right? 2, what happened if we do 2? The area we find is going to be up to 2. There, right? So now the area is going to be this piece of area and all of these up to 2. The area is the function. But now about G of x? How about G of x? Right? How about G of x? And now I'm going to clean this up. I'm going to show you what is g of x. Right? So you can see g, first of all, it is a function. How it is a function for each input, right? The input would derive a function from 0 to x, and the f curve, you know, the area underneath the curve, and each input is exactly one output. Each input exactly one output. Each input exactly one output. So that's the g function, but g function is the area underneath the curve for f. Now, how about the g in general? How about this piece? How about this function? Well, in this particular case, we can replace the f of t. We're going to put f of t in place, right? F of t is this function. And we know that function has an antiderivative. So we put this in, and we're going to find the antiderivative. Okay, so let's see, what is the antiderivative? We already found it once, right? We already found it once. We found it once, and according to fundamental theorem of calculus part 2, we can evaluate according to fundamental theorem of calculus part 2. And what does that mean? We're going to plug in. We're going to plug in, replace the t by, so for this piece, t equals to x. For this piece, t equals to 0, right? And the former will give us the following: t replaced by x, t replaced by x, t replaced by x. That part t replaced by 0, that whole thing is going to be 0. So this is g. So g function actually is this piece. This is g function. This is the g function in this example. Now, the fundamental theorem of calculus part 1 basically says if I take a derivative of g, it's going to equals to f of x. So we're going to verify if this is true. It is not a proof. Okay, the proof is something else. The proof is something else. If we have time, we can do it. We can prove it, but if not, we can prove it another time. But so you can see we follow the steps, we constructed g, and g is such. And next we're going to take a derivative of g. What is the derivative of g? The derivative of the g, then we follow the rule of the derivative, right? So we have 1/3 multiply 3 times x squared. That's the derivative. Plus 4x minus 1. If we organize the term, we get exactly what f is. We had f of t, but f of x, if we replace the t by x, right, what is f of t? What is our f of t? This is our f of t. Right? This is our f of t. F of t, right? If I replace t by x, that's f of x. Same thing. That's what the theorem says. Okay? Now, what if f is some function, some other function? Well, no matter what function f is, mathematicians have proved that it's always the case. It's not only true for this case, it's also true for other cases. Now, let's look at another situation. Example number 2. suppose I'm going to compose G, right, with a composite function. So right, so I have a G here. I compose G this way, but I can also compose G some other ways, right? Suppose I have a G of sine X, then this will be what? Sine X. Then what I do? If I want to find derivative, right? If I want to find derivative of G in this new function, what do I do? What do I do? Right? Well, first of all, you will see this function. Then suppose we just go back there. Okay, so let's go back there. We go, we still use the same f of t. We still use the same f of t. Okay, we use the same f of t. No problem. And because we know the antiderivative, we already know what a G is. So G, this is a G, right? G of sine X, and this will be G of sine X. And this is a G of sine X. And this is going to be sine X. This is a G of sine X. How do we find the derivative of this function? Right? G of sine X. What would that be? You can do it two ways. If you can work with this one directly, right? One way to do it. If you know what G is, right? And that will be, you take a derivative of each one of them. Of course, we're going to use a chain rule. -1/3 of, and this is going to be sine square X, right? Multiply, you have to differentiate the sign, right? That's going to be cosine X. On the second part, chain rule again, so we're going to have 4 times sine X and cosine X. And the lastly is cosine X. So if we simplify this expression, we factor out the cosine X. We factored out the, oh wait, we have a 3 here, sorry. Or 3 times, okay, because this, we're going to differentiate the sine to the power of 3x, okay? So now we're going to simply, this is going to be negative, right? We're going to factor out the cosine x, right? So this is 1, all of these. Multiply cosine x. So the derivative of g of sine x is going to be this piece, which we differentiated g, right? We differentiated g. This is really is what? What is this? What is this? This is really, okay, it's really f of sine x multiply cosine x. Do you see that? Because this is f, right? This is f. This is f, right? But when you substitute t with sine x, and this will be what? Sine x, and this is going to be sine x, right? Aren't these two the same? So that's how this f of sine x. chain rule is applied. So that's one way to do it. This way of doing it is that if you know you already found the G. What if I didn't find the G? Right? If I don't know G, for example, I can still do it. I'm going to still differentiate using chain rule. Right? Using chain rule. Because in this case, I don't really need to know G in order to find the derivative. So what I would do is I would do G of U. G of U, where U is sine X. And with respect to du, multiply derivative with respect to u dx. And of course, u is what? U is sine X. Now, this is derivative of g with respect to u. What's the derivative of u with respect to derivative g of u with respect to du? Well, we already have the fundamental theorem of calculus part 1 here. This piece. Okay, this piece. What does this piece say? Okay, let me bring this piece under. Okay, I put it under. What does it say? It says the derivative of g with respect to x. So the derivative, so this is a g of u. G prime of u, g prime of x. And of course, this is a cosine x, right? G prime of u is f of u. Is f of u. Multiply cosine x. And what is u? It's f of sine x. Multiply cosine x. Okay, so this is one interpretation of it. This is one, I hope this helps. Okay, I hope this helps. Another interpretation, which I was, I had a discussion with one of you, and he brought in some, this student brought in some other ideas from other places. I think I will combine his interpretation and his, work. I understand that work, but I will give I think it's probably even simpler interpretation. Okay, probably even simpler interpretation is that why we, and I'm going to also talk about the examples we did, the quiz question on. First of all, fundamental theorem of calculus part 1, I have been emphasizing the relationship between G and F. Okay, this relationship basically says, right? This relationship basically says this. It says G prime of x equals to f of x. By the definition of antiderivative, please look up what is the definition of antiderivative. I'm going to look it up. I'm going to bring that definition from the textbook directly to you. Okay. While you are also looking for that definition, it should be in section 4.9. Okay, where we have introduced the definition of antiderivative. Okay, hold on. I hope by this time you have found the definition of antiderivative. What is the definition of antiderivative? Come on. I'm going through the textbook. I know it's in section 4.9. Let me grab the page number. It's on page 350. Okay, so I found it. 350. Okay, on page 350, if you use version number 8. Okay, so I'm going to copy and paste. I'm going to copy this. I'm going to screenshot this definition and show it in front of you. Okay, the definition of antiderivative. It's very important to follow these definitions, really, right? Because once we know what is what, and it's clear and no ambiguity, and this will be very helpful. Definition of function capital F is called an antiderivative of F on an interval I if the derivative of capital F is the same as the lowercase f of x. And we're fitting in that, and G is fitting for that definition. So G is a capital F, right? G is a capital F. So G, because it's antiderivative, right? So let me write down some word. G is an antiderivative. Derivative of what? Of F. It's a lowercase f. Okay. If G is an antiderivative of capital F, right? So what we can do when we are doing working with in our current example, right? In our current example, we have f of t. I'm going to use f of x. It doesn't make any difference, okay? Because f of t, if you replace t by f by x, is x. So this is f of x, and we have even found the antiderivative. G of x was found, right? And obviously that is, we have verified G of x is such. G of x is such. What we want to use is that in this case, okay, yeah, in some other cases, sometimes G is not known. G is not known or very difficult to find. Okay, such as in our example, in the homework question we have today on the quiz. Okay, so here's the question. Okay, I'm bringing the homework question to illustrate for you. Okay, just 1 second. I'm going to bring that homework question in front of us. Oh, hold on. I'm sorry, that quiz question. The function we have is y equals to sine. There is a lower bound, and the upper bound sine x, and the upper bound is 1. And we have a function square root of 1 plus t squared. Okay. Okay, and we did that swapping, right? And so this is going to be 1, and this is going to be sine x. So it's positive 1. Okay, so we have that situation. In this case, right, the integration of this function is a little hard to find. It's a little hard to find. Why? Because it's hard to find the antiderivative of square root of 1 plus t squared. At least not yet. Okay, and that's common. Sometimes it's very hard. But even though we don't know that, but because we just want to know dy dx, don't forget what we want. We want to find the derivative of y. So we're taking derivative of this function, i.e., that function. We want to take a derivative of this function. And let's see how we're going to resolve this, right? The negative sign, we just leave it out. Negative sign, we just leave it out, right? So in this case, we look at this function. How is that related to our functions? For example, if I construct a g, right? If I call this g of x equals to that piece, right? Without the sign x, just x. Then what is a g of sine x? You see, there's a correspondence here, right? There's a correspondence here. So g of sine x and that will be sine x. In order to find the derivative, of d of sine x, so this question now it turned into what? It turned into derivative of g of sine x. G of sine x. Okay. Now, fundamental theorem of calculus tell us something. Tell us some stuff. Okay. The fundamental theorem of calculus part 1 tell us some stuff. And what are those stuff that we're being told? What are those stuff they're being told? Right? Derivative. Right. So this is the function we are familiar with, right? So we already used that. So I'm going to bring up, put this away. This derivative, we know that this derivative by fundamental theorem of calculus part 1, let me bring that up to you. From 1 to x, from a to x, f of t is this piece, right? So f of t is root 1 plus t squared. Okay, so let me leave some space. Okay, so according to fundamental theorem of calculus part 1, when we construct a function like this, the derivative of g of x is going to be f of x. It's guaranteed. Guaranteed. And as we said earlier, right? As we said earlier, g is, this says g is the antiderivative. G of x is an antiderivative. I didn't say the, because once you have antiderivative, you have many of f. G is antiderivative of f. If g is antiderivative of f, right? Our f is such, we don't know how G look like. Okay, in this case, we don't know how G look like, but I do know G, right? When I integrate this and this piece, I'm going to use this f of t, right? It has an antiderivative, and that antiderivative is G of t, right? And that's going to be evaluated. This is according to fundamental theorem of calculus part 1. That'll be evaluated at 1 and at x. Right? And now what if this piece is from 1 to sine x? And this is 1 to sine x. And that's going to be what? G of sine x subtracting G of 1. Okay? So now our goal is to take a derivative of this piece, right? That's our y, right? That's our y. So I'm going to take a derivative. So put a negative sign on each side. So let me let's first just take a derivative, because y is something else. So we take a derivative of this piece, and we're taking derivative on the other side. The derivative of G of 1 is going to be 0, right? It's a constant. And so we take a derivative of that piece, derivative dx, and we're taking derivative of that piece, right? And which is the same as taking derivative of G of sine x. It's a composition. So the taking derivative of this piece is the same as taking derivative of the other piece, G of sine x. And then we're going to use a chain rule. Okay, so G of u, take derivative of G of u, and then u dx. U dx. And u is sine x. And this is du. Okay, and the derivative of d, we already have it. This is a g prime u. This is a g prime u. Okay, this is a g prime u. And the derivative of sine x, of course, is a cosine x. G prime u is f of u, right? G prime x is f of x, G prime u is f of u. So this piece is going to be f of u. F of u equals to, and that's multiply cosine x. Okay, and by this time we're close, because this function is a sign different from the y we're looking for. So we bring this into the picture. We bring this into the picture, right? So when we are doing dy dx, right? D dx, and we're taking derivative of all of that. And we have worked out this piece, right? We worked out this piece. Now this piece is worked out, we just have an extra negative sign, and that equals to f of u, right? And of course, f of u is sine x. U is sine x. And then last but not least, you're going to have f of sine x. We have, we know what f is, right? This is f of sine. We bring that closer to us. So f of sine x. So that's going to be f of sine x. Okay, so in the end, we get negative of that multiply cosine x. Okay, so this is the other interpretation, which I referenced to the other student brought in. However, the way I have been talking about is this. The way I've been talking about is the following. Okay. Suppose we still do the same question. Okay, this has been a bit too long. Okay, so we're taking derivative. If I am to take a derivative, so hopefully by this time you can see that piece is just a function. This piece is a function. Okay, so when I do dy dx, okay, I'm going to take a derivative. We'll put a negative sign. So derivative dx, right? We bring this in. And this function, okay, this function is really the g for sine x. Okay, so what I did is I keep it this way. I make this u, okay, and du multiply du dx. And the u, of course, is sine x. Okay, you can do it this way, which I used to teach. And the other thing, and then of course, for this part, right? For this part is a derivative u du, g of u, multiply that piece, of course, that's the cosine x. Right? This is a g of u. This is a g of u. G of x, let me show you. I know it's a little bit difficult to read it. Okay. G of x. Okay. G is this piece. So when this is u, this is a u. Okay. And when this is x, this is x. So g derivative with respect to x is equals to f of x, right? If you change this all to u, if you change x to u, same thing, because these symbols are merely placeholder. They're merely placeholder. So g, the derivative g prime u so this is a g prime u. G prime u is f of u. So g prime u is f of u. Okay, so you would end up with the same answer. You end up with the same answer. So this is going to be negative root 1 plus sine square of u, sine square of x, I'm sorry, multiply cosine x. And for simplicity, you can, and less confusion, you could bring that cosine x to the front. Okay, now to summarize, I'm going to give you a final version, which I highly recommend. I think might be just make life just a little bit simpler. Okay, make life simpler. So when you encounter a question like this, right? Like for this quiz, we want to find the derivative. Okay, we want, so y is given. Okay. Quiz question again. Again. What is the simplest thing you can do? What is the easiest thing to do you can do? That's also, you know, make things simpler. What is wanted here, and we're going to do another example. Okay, what is wanted here is dy dx. Right? dy dx. dy dx, we're going to take a derivative, right? So we first need, sometimes you need to do some preliminary work. dy dx is derivative dx of that piece. How do you see that piece? Okay, what I would do, I would introduce a g of x. A g of x. G of x is this piece. This is my x. And as a result, this piece is taking derivative of g of sine x. Do we know how to take a derivative of g of sine x? Of course. We use a chain rule, right? So we take this piece and we change this to u, and du multiply du dx. U is sine x. So that way, so this now, this piece is g prime. G prime u multiply cosine x. G prime u. What is G prime u? Right? According to fundamental theorem of calculus part 1, let me bring this over again. G prime u is f of u, right? So G prime u is f of u, right? And of course, you also we have identified what is f, right? F of t equals to that piece. So G prime u is f of u, and f of u is replacing this piece by u. So this is u squared. And G prime u is f of u, and so f of u is going to replace that piece. I know that's quite a bit, but I hope I have made it a bit easier. I made it a bit easier. Okay, so this is a sine x squared plus cosine x. Have I achieved my goal? I hope so. I hope so. But there is a proof of this theorem for fundamental theorem of calculus part 1 in the textbook. And I to avoid making this recording too long, we probably save it for another time. We save it for another time if we have time. But so far, I think this latter version is a kind of a combination between what I used to teach and the fresh air, or you can the other way that the other professor talk about. So last but not least, I'm going to do an example from your homework. Okay, and this example hopefully will bring some fresh air. Okay. So another example. Okay. The other example is y equals to integration from 0 to x to the power 4. X to the power 4. And the function in consideration is cosine square theta. Cosine square theta. D theta. Even though we can find the antiderivative cosine square theta, but we're not going to do it this time because we don't need it. We don't need to do it. You will learn those techniques in your calculus 2 class. So what's wanted, right? Wanted is we want to find dy dx. Dy dx. Okay, we want to find the derivative of this function. Okay. So now, in order to find the derivative of this function, then we look at this function, right? So what I would do is that I know the fundamental theorem of calculus part 1, right? Knowing that, I know my f of theta, right? You compare these two forms. So a is 0, and we don't have a simple x, we have x to the power 4. So it's a compositional function. So I'm going to compose my g of x. As is said in the theorem. G of x is going to be cosine square theta. So I better use g of theta, isn't it? You know, it's just, if you have that g of theta, if you use a g of theta or use g of t, then this is a t. It doesn't really matter. It's just a placeholder, right? I don't use x because I don't want to cause any confusion. So now I use theta, so this is just theta. Right? Same thing. No difference. Okay, no difference. It's a placeholder. So my g of theta is a cosine square theta. And now what is this? If g, I'm sorry, I didn't finish. Okay. Integration right here. Integration from 0 to x d theta. This is my g of theta. You see, my g of theta is made in similar manner as in the theorem. 0 to x, a to x. And this will be x. Okay. My bad. And f of theta is equals to cosine square theta. I think I said something might be confusing just a bit earlier. It was G, okay? I said it about G, so I'll take it back. Let me do it again. Okay, let me say it again. I make a G of X in the same manner as the fundamental theorem of calculus part 1 says. G of X is the integration from a constant to X and whatever function that is. And that function I have identified is f of theta, right? So f of theta is identified. All right, you can see I have a matching, I have a match, perfect matching. Okay, perfect matching, hopefully. I think it is. Okay, so this whole piece is G of X. F of theta is this piece. So under this, and of course the function is f is continuous, right? Cosine square is a continuous function. So according to this fundamental theorem of calculus, G prime of X is equal to f of X. Okay, so we have all of these prepared. Now, what do we want? We want to find the derivative of this piece. And what is y? By this time, you can see under these assumptions, y is d of x to the power of 4. Okay? And we want to find the derivative of it. So when we want to find dy dx, this is really just to find the derivative of g of x raised to the power of 4. It's a composition, right? And then we just go about it. So this is going to be u du multiply du dx. U is x to the power 4. And for that piece, is g prime of u. G prime of u. And the derivative of x to the power 4 is 4 times x raised to the power 3. Right? And the g prime of u equals what? G prime of u is this piece. G prime of x, that, so g prime of u, it just, you simply replace u by, it's just f of u. And multiply 4x to the power 3. You can put it in front if you want. Right? And what is f of u? What is f of u? F of u, well, you know what is f of theta is, right? So f of u is just simply replace theta by u. F of theta is a cosine square theta. And f of u is going to be cosine square of u. And what is u? U is x to the power 4. U is x to the power 4. Boom. Finished. Finished. Well, we talk about different versions, lots of information. When you watch this, please, you may need to watch it again. Make sure you have paper, pencil, right, with you and follow along. And if you have any other questions, please don't hesitate to reach out to me. And thank you for watching.